So for this video, we're going to be talking about more on functions and their graphs, specifically talking about increasing, decreasing constant functions. We're also going to be doing testing for symmetry, looking at even odd functions, y-axis, x-axis, origin symmetry. We're also going to take a look at some piecewise functions, specifically just evaluating from piecewise functions. We'll talk about graphing those in a different video. And then we are ending this video here with the difference quotient. So let's go ahead and get started here. So I know these graphs are a little bit small, but we mainly just need to look at the motion of these graphs here. So whenever we determine where a function is increasing, decreasing, or constant, we will label that using interval notation, open-ended interval notation. So every single one of these examples here does have open dots on either end. So for their interval notation, we will be using parentheses solely for this particular type of problem here. Otherwise, an increasing function essentially has a positive slope. Anytime we look at graphs in math, you always want to get in the habit of looking at the graphs from left to right, bottom to top. So looking left to right, if we're going up, uphill, upstairs, positive slope, that is an increasing function. Going downstairs, downhill, right, negative slope, that is a decreasing function. If we're not going up, if we're not going down, if we're just staying straight and steady, a horizontal line, that is what a constant function looks like. I apologize, I just realized I did not have my graphs drawn on here. Now we are ready to jump into these two examples. Let's use the following graphs to determine which intervals the following function is increasing, decreasing, or constant here. So when it comes to these type of problems here, I always say if you're having a hard time picturing it, always kind of pretend that you are standing on the graph and that you're going to walk across this graph. Where would you be walking? Now again, using graphs, looking at them left to right, we would start walking this direction here, right? So we'd be starting this graph by walking up, 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 up. And once we got to this point right here, we're going to take a dip and we're going to be going downwards, which means from here to here, that is an increasing graph. We're going upstairs, uphill. From this point here, we're going to turn around and we are going to decrease. We're going downhill, downstairs. So for this particular graph, we only have increasing and decreasing. We do not have a constant section, which is perfectly fine. You might not have all three. You might just have one. Keep in mind that we are using interval notation to write our intervals here. So that is based off of our domain, our x-axis. Arrow on the left-hand side means that this graph is coming from that direction. That is a negative infinity. So from negative infinity up until this point right here, that is our decreasing section. The x value for this is a -2. So from negative infinity to -2, this portion right over here, that is where we are increasing. At this point here, at that -2, this is where we would turn around. So this is the start for our decreasing now. So we're going to say we're decreasing from a -2, and then we're going to keep decreasing, and we're never going to stop. That arrow there tells us that is going to be a positive infinity. So increasing from negative infinity to -2, decreasing from -2 on to positive infinity. Taking a look at the next example, do the same thing. Picturing yourself walking across this graph, moving left to right. Our graph starts at this point here. And at this point, we'd be walking straight, straight, straight. Keep in mind that is a constant, that's a constant interval right over there. So we'd stay constant, constant. From this point here, it looks like we have a slight increase. So we are going to have an incline going up. So we are increasing from here to here. At this point, it looks like we're going to have a decline and we're going to start decreasing there. So for this particular example, we do have all three, increasing, decreasing, and constant. Starting on the left, so this point here looks like a -3. And it looks like from a -3 to a -1 is where we would be constant, right? That is our horizontal part here. Starting at the -1, we have a positive slope, so that is increasing. So starting at -1 to over here, that looks to be a +2, we are increasing. And then starting at that positive 2 is when we're going to start going down. And with that arrow at the end, that means from positive 2 to infinity is going to be our decreasing interval. For our next portion, we're going to be talking about testing for symmetry. So there are 3 different types of symmetries that we can have. We can have a y-axis symmetry, which is also known as an even function. A y-axis symmetry is typically going to be things maybe like an absolute value graph, some parabolas here. It means that if you were to take this y-axis and fold it on itself, so literally think about folding it across the y-axis like that. If everything on the left matches with everything on the right, if they are symmetrical on either side, then it is an even function. The test that we do for equations is, does f of x equal f of negative x? There's also x-axis symmetry. So x-axis symmetry means that if you're going to fold it on your x-axis, the top and bottom side would match. So if we're going to fold it this way, right, in with each other like that, if we fold it across the x-axis, would the top and the bottom parts match? So this would maybe be an example of x-axis. If we folded it on this line, this part would match up with this part. There is also origin symmetry. Origin symmetry is also called an odd function here. Origin symmetry is going to be something like maybe a cubic function. It is, think of it as a fold across your x-axis and a fold across your y-axis. So you're going to fold it vertically. You're also going to fold it horizontally. So think about taking a piece of paper and folding it into a corner, right? You're going to fold it twice to where you have a fourth of the page showing. So that's kind of what's going on with origin symmetry. The test for origin symmetry says, does f of negative x equal negative f of x? So let's go ahead and jump right into these examples here. We are going to test all 3 symmetries for these examples here. So starting with an even function. So a lot of the times when it comes to symmetry, you're either asked, is it an even or an odd function? If so, it's just specifically talking about, does it have y-axis symmetry? Does it have origin symmetry? Sometimes you might be asked all 3. Does it have y-axis? Does it have x-axis? Does it have origin? So kind of just pay attention to the instructions of the problem you're working with. So let's figure out what type of symmetry these examples have. So starting with y-axis symmetry, does f of x, right? F of x, our original function right over here, does it equal the same thing that we would get if we were to plug in a negative x for it? So if I took this exact function and I took this x and replaced it with a negative x, would I get the same thing? Well, when I simplify this, let's see, I get y is equal to, well, negative x squared. Negative x times negative x is x squared minus 1. Does this equal the original function? Well, I don't know about you, but they look exactly the same to me. Y equals x squared minus 1. They do equal each other, so that means that this function does have y-axis symmetry. It is an even function. We are next going to test to see if it has x-axis symmetry. We are going to replace y with negative y, or take the opposite of the function here. So let's see, we would take our original function here. We are going to replace y with negative y here. Now, if we're going to take y, replace it with negative y, let's simplify this function. Let's multiply or divide everything by a negative 1 so we can get rid of this negative here. So if we do that, we're going to get y is equal to negative x squared plus 1. Is that the same thing as your original function? Now, they look very similar. Y is equal to, well, this is where they change, right? This is a positive x squared. We have negative. This is negative 1. We have positive. So this does not have x-axis symmetry, which also means it does not have origin symmetry. This one is simply an even function. It has y-axis symmetry. Moving on to the next example. So let's just go through the list. Let's check y-axis first. Let's replace x with negative x. Now we can take this x here, plug in a negative x instead, and simplify. If we clear out that negative, there we are left with x is equal to negative y squared plus 1. These are not the same thing, right? So y-axis symmetry does not work there. Let's replace y with negative y to see if the x-axis symmetry works. So take the same function, x is equal to our y squared minus 1, where y is now going to be a negative y. When we simplify this, x is equal to negative y times negative y is y squared minus 1. So compare that to your original. X equals y squared minus 1. That is the same thing, which means yes, this does have x-axis symmetry. And it will only have x-axis symmetry. Origin will not work here. Again, origin, it has to be a yes for y-axis, a yes for x, and it's going to have its origin here. Checking the last example here. So let's replace, all right, let's check y-axis symmetry, replace x with negative x, and see what we get. If we replace x with negative x, well, simplifying this, negative x times negative x is x squared. And we are left with the same thing as the original. They are both x squared plus y squared is equal to 25. So that means y-axis symmetry does work. Let's check x-axis symmetry. X-axis symmetry, replace y with negative y. And we can see here when we do simplify, negative y times negative y is y squared, and that's going to equal 25. That is equal to the original function here. Origin symmetry, so an origin symmetry or an odd function is the both of them together. It says, does f of negative x equal negative f of x here? So f of negative x, we just did that here. We plugged in a negative x right over here, and we tested it. So this is right here, this is what f of negative x is equal to. We plugged in negative x, we got this. So we are testing to see, is this the same thing as negative f of x? So you can think of it as taking the opposite of a function, or since it is a combination of the two, many descriptions for origin tell you to replace x with negative x, replace y with negative y. Do both of these here for this example here. If I plugged in a negative x for x and plugged in a negative y for y, do I get the same thing as f of negative x here, or the original equation essentially? Well, when we clear these out, we are left with x squared plus y squared is equal to 25. So we do get the same thing. So that means this is an odd function. Right, it has origin symmetry. The next thing in this section is evaluating a piecewise function. So in evaluating a piecewise function, keep in mind a piecewise function is a function defined by two or more equations. So we're just talking about 2, 3, 4, 5, however many equations kind of thrown into one. Now, this particular example is telling us that f of x is equal to this top equation, 3x plus 5, when x is less than 0. It's equal to 4x plus 7 when x is greater than or equal to 0. All right, so kind of think about it this way. So this is not going to be drawn exactly like this here, but they're telling us to the left of 0, this graph is going to look one way. To the right of 0, it's going to look a different way. So they might not necessarily connect here, but they gave us 0 kind of like as a barrier. And they're saying on the left side, when you're less than 0, it's going to be this top equation. To the right side, it's going to be whatever this bottom equation is here. All right, so you're piecing two equations together. Now, we're only going to be evaluating these right over here. So our first question, find f of negative 2. Now, it's important, the first thing that you need to do is take a look at that negative 2 and find which one of these equations negative 2 falls in. Again, you want to look at your parameters over here. Is negative 2 less than 0, or is it greater than or equal to 0? Now, negative 2 is definitely less than 0. That's going to apply to this top one. So we are going to evaluate this top function for negative 2. We're literally just going to take that 3x plus 5, where our x is now a negative 2, and we have our 3x plus 5. Simplify that. 3 times negative 2 is a negative 6, and a negative 6 plus 5 gives us a negative 1. Taking f of 3, again, go back to your stipulations. Which interval does that fall in? We have a positive 3. Well, positive 3 is greater than or equal to 0, so we'll be evaluating the bottom function there for a positive 3. So plug in a positive 3 in for x and simplify. 4 times 3 is a 12, and 12 plus 7 does give us a 19 there. Our last two examples are going to focus on the difference quotient. So the difference quotient, you tend to see this problem a little bit more the further that you move up in math. Definitely when you move on to pre-cal, anyone moving on to calculus or anything like that, you'll start to see the difference quotient a little bit more. This is the formula for the difference quotient here. So it takes a couple of pieces to put this together. If we take a look at this formula, it's asking us to take f of x plus h, subtract f of x away from it, and then divide everything by h. So before I do anything else, what I always do is I always start by finding what is f of x plus h. Right, they give us f of x, but we need to find f of x plus h, which means we're going to substitute, right? We're going to take this x, replace it with x plus h instead. That's going to look like our 6x plus 1, where x is an x plus h. Simplify this. Distribute the 6 to get 6x plus 6h plus 1. There's no simplifying or anything to do here, so this is what f of x plus h is equal to. Let's try and put everything together here. So according to our formula, f of x plus h goes first, so that's what we just found. 6x plus 6h plus 1. We are going to subtract away f of x. So make sure you do put f of x in parentheses. We are subtracting the whole thing away. Our f of x, our original function, is 6x plus 1. And before I put that all over h, let me go ahead and just simplify this here. Right, this will all go over h according to our formula here. But because we do have this minus sign in front of these parentheses, let's go ahead and distribute that here to give us 6x plus 6h plus 1. Distributing that minus sign gives us minus 6x plus 1. And this will all go over h for our full function here. Let's simplify what we can. We can combine some like terms. 6x minus 6x disappears. We get a 0 there. And, oh, I'm sorry. I just realized I did not distribute that negative all the way. That should be a minus 6x and a minus 1. My bad there. So that means this positive 1 does cancel with this negative 1. That means the only thing we have left in the numerator is a 6h over that h. Rules of factoring, or just if you have the same thing in the numerator as you have in your denominator, it cancels out to a 1. And 6 times a 1 is just a 6 that we get there. You will find a lot of times once you put the formula together, a lot of things do tend to cancel out. So let's go ahead and work this next example so we can see what happens here. I'm going to start it off the same way by finding f of x plus h. So let's see. 2x squared minus x plus 3, where x is x plus h. Let's simplify this. So let's see. First thing we need to do is we need to square this binomial here. So we can do x plus h times x plus h. Let's distribute that. X times x, because it's x squared. X times h, that's hx. Put that in ABC order. Distribute the h to get another hx, and then h times h is h squared. Combine your two middle terms, and we get x squared plus 2hx plus h squared. So let's go ahead and throw that in here. X squared plus 2hx plus h squared. Minus, let's go ahead and distribute that minus sign. Minus x minus h plus 3. Let's distribute this 2 here, and that is going to give us 2x squared plus 4hx plus 2h squared minus x minus h plus 3. So that represents just the f of x plus h here. So the first part here, 2x squared plus 4hx plus 2h squared minus x minus h plus 3, minus our f of x. So if you don't mind, I'm going to go ahead and distribute the negative on that as well, so I can just have everything in the same line together. All right, so we are subtracting f of x. That would make that a negative 2x squared, a positive x, and a negative 3. So that is a minus 2x squared, a plus x, and a minus 3 all over h. Let's see what cancels. I see a 2x squared that cancels with a negative 2x squared. Let's see. Negative x cancels with the positive x. Positive 3 cancels with negative 3. And I believe that is it. So what we have left over is a 4hx plus 2h squared minus h all over h. We can still simplify this just a little bit more here. Notice that every single term that we have in our problem has an h. Let's factor out an h from that numerator. And if we factor out an h, we are left with a 4x there in front, plus 2h minus a 1, all over h. That way that this h can cancel with this h, leaving us with 4x plus 2h minus 1.